Hello and welcome to my presentation on design for additive manufacturing. Now there's lots of additive manufacturing processes that are available, as a multitude have appeared and many have grown over these last 30 years. It's become quite popular, actually. Now polymer is much more common for additive manufacturing, but metal is also taking off. Now some of these processes that are available include powder bed fusion, plastic extrusion, and photopolymerization for polymers, and laser powder bed fusion, electron beam melting, and metal binder jetting for metal additive manufacturing. So whenever you're considering using metal or just additive manufacturing in general, you need to first justify using it on your parts. Now one of these best ways to justify it is to justify it with economics. At very low quantities, it's apparent that additive manufacturing is often the way to go. But once you start making these parts in significant numbers, like at a production level, traditional manufacturing methods often overtake additive manufacturing. Another way that you can justify use of additive manufacturing is with design complexity. If your design is simply too difficult to make using traditional manufacturing methods or other sorts of machining or CNC, then additive manufacturing might be the only way to go. When designing for additive manufacturing, one of the guidelines that you want to keep in mind is minimization of material, because you pay for the amount of material that you use, and the amount of material that's there is how long it's going to take to print as well. So the more material there is, the longer it generally takes to print. This is also dependent on orientation, but that is an important factor to consider. For polymers, it's common for there to be some level of anisotropy whenever you print. Now, here is a good example of just a clip that was 3D printed, and it seems like this was printed using an extrusion method for polymers. So the first one, it mostly allows the force to be along that length of the clip. Now there's limited adhesion between the layers here because of the method, and so that means that this first option is likely to break very easily. The middle option actually seems to be the best option, whereas the last one would probably break where it is mounted. Some general rules for polymer additive manufacturing are to keep a uniform thickness to minimize distortion, to reduce the surface area molten at once also to minimize distortion, adjust the infill to minimize the amount of material required, but also provide that same amount of strength that you need, so at least meet your design requirements using your infill strength. And also adjust supports so that you use less material. This would be accomplished by using sparser supports near the base, and as you go up towards the features that you need to print, then you would make that support more dense. And this gives you a good finish on your part once it gets up to there and starts printing what you need, but lets you use less material to get up there. Now, let's cover the bed fusion method for polymer additive manufacturing. This is when polymer powder is sintered, and it's sintered often using a laser or some other concentrated form of energy, and it's going to sinter these particles of polymer powder together. It's actually quite good at avoiding anisotropy, although it still has some, but it's better than some of these other methods because that heat penetrates to the layer or region below, and now this new layer actually is adhered well to the previous layer. An interesting concept for powder bed fusion is that with this buildup of powder at each level, you can actually print overhangs quite easily because that powder will support the material that you want to print. However, the drawback here is that you get a rough finish, which is pretty much equivalent towards the powder sandy finish that you had put into the machine to begin with. These are some of the accuracy and tolerances for bed fusion, and it's limited by its finish there, really. When considering additive manufacturing and specific methods, you often want to look at specific design features and how the method affects them. This way you can incorporate the design requirements so that your part will turn out correctly with a given method. Here's an example of the feature for wall thickness with the powder bed additive manufacturing for polymers. There's also clearance between moving parts as a feature, clearance for a circular profile, square profile, circular pins, hole proximity to a wall edge, and that leads us into polymer additive manufacturing with plastic extrusion. This is actually the most common method, although it exhibits somewhat weak layer adhesion. This was like what I mentioned with the clip earlier. And design progress or research progress has allowed decent tolerances for this method. Metal additive manufacturing is kind of on a different level than polymer additive manufacturing. That's mostly due to the heat that is required to actually obtain a metal part. Now, this heat comes with the major drawback of residual stress. Whenever you heat an area of metal very quickly and let it cool, that's going to introduce lots of different thermal stresses into your part. Supports are extremely important for metal additive manufacturing, and this is because they serve many functions, including strengthening of parts, fixing parts to the build platform, conducting heat away from the parts, preventing warping, and resisting the mechanical force of the powder spreader. In this figure here on the right, you can see that this is a powder bed method. Looks like laser sintering, and as you increase the angle, less support is needed generally, and the cutoff here is 45 degrees, where it starts becoming more needed as you decrease that angle from the horizontal after that. So residual stress, like I mentioned, is a big issue and actually the cause of most warping and issues with metal additively manufactured parts. So how do you minimize the risks of residual stress? Well, first you can use a uniform thickness, avoid large changes in cross-section area, preheat the build plate, preheat the build chamber, and you can incorporate chessboard hatch patterns. Here is an illustration of those chessboard hatch patterns that I just mentioned. So what they do essentially is they allow the different residual forces to face different directions, and so overall they don't accumulate like they would in the meander hatch pattern or the stripe hatch pattern. So they're in all these different directions. You can think of a magnet and how those little particles, when they line up the grains in all the same direction, you get a large magnetic field around it. But if they're all in their different directions, then you get a much lower magnetic field, if any at all. And so this sort of method can decrease the amount of residual stress with the drawback of taking longer to accomplish. Now here's some guidelines about support design. I attended a thesis defense from Lucas Moran, and he provided some guidelines for support options. So his slides are shown here, where he identified some key points on where supports are needed. And he shows us all the different kinds of support options, and you see here that for those different supports they have sort of serrated edges when they're attaching to the part, and this is to minimize the amount that's actually connected to the part and make it easier to remove. because you do have to remove this metal from the metal parts, which can be a significant cost for just post-processing these parts that are additively manufactured. Also, they're put into plates to decrease the amount of time that it takes and make it easier to get rid of those support materials. These were the results that he obtained from those different support options. Now onto the metal additive manufacturing methods. Some of those include laser powder bed fusion, electron beam melting, and metal binder jetting. So for laser powder bed fusion, it's similar to polymer bed fusion, although it requires support material, which is unfortunate here, and it has very specific guidelines because of that support that's required. Remember those residual stresses, and it has guidelines for the features similar to what we showed for that laser bed sintering earlier, shown in reference 1 if interested. Electron beam melting uses the electron beam as an energy source, although it also has a powder bed. This electron beam is controlled with electromagnets, and one of the important distinctions between this and the previous method was that it requires partial sintering of all of the powder that's on the build plate. So this means that that powder is actually going to provide some support and wick away heat better than in the laser melting method, so less support is required. The final method we're going to cover is metal binder jetting, and this is when you have many thin layers of metal powder printed with a binding agent. After printing this part, it is removed and it's called a green part. Then it's debinded, cleaned, then sintered or infiltrated. Sintering, of course, being heating to the point where the particles mush together and combine, or infiltration, which is actually the incorporation of an alloy into the part. Kind of like casting, but with the 3D printed part. And one example alloy that's used for that is bronze or brass. This method has some issues with shrinkage and specific guidelines to avoid shrinkage within source 1. Here are the references. Thank you for watching, and if you have any questions, feel free to leave them in the comments.